Okay, so far we have been talking about the electric field of discrete charges, and now we will, however, in reality, of course, the charges are not scattered as single point charges, but they are distributed actually continuously over lines or surfaces over within volumes. Now we will see how we can find the electric field of these continuous charge distributions. Now, when the distances between charges and a group of charges are much smaller than the distance between the group and a point interest, then we can be modeled as continuous. The charges in this case can be modeled as continuous. I mean, at the end, continuous charge distribution is actually a collection of point charges, but when the distances between them is much smaller than the distance at which we want to find the field, then we can think of them as being a continuum, forming a continuum rather than discrete points. Now, in this case, we can think of this system as being a total charge that is distributed over a line or a surface or a volume. Now, how do we find the electric field of such continuous charge distributions? The procedure involves integration at the end, as you will see, but it's quite intuitive and it's easy to grasp, and it's also based on the idea of linear superposition that we have described before. So first we divide the continuous charge distribution into infinitesimal portions. So as you can see here, we defined this is a charge that is distributed over some region in space, okay? And we divide this into small delta Qs so that these delta Qs can be treated as point charges. So the whole thing, I'm showing here a few of them, but the whole thing is divided into these small delta Qs. So this is the first thing, okay? Then you find the electric field of one of these delta Qs and write down the expression for that. So for example, for any point charge here at this point P, the electric field delta E is K delta Q over R square R. Okay? This is the expression for the electric field of any one of these at this point P. Now, the total electric field at this point will be the superposition given by the linear superposition of the electric field of all the dQs that you have taken to cover the whole charge distribution. And so you form this sum. Okay? Sum over delta Qi over R square R hat, and this is summed over all these charges. Now, the ideal situation is when we make these delta Qs very small. What do you mean by very small? As small as a point, okay? And this means you take delta Qi equal to 0. And so their number in this case becomes infinite. So evaluate this sum in the limit. Of course, this is a vector sum. In the limit when delta Qi, that is the size of each of these point charges, goes to 0, or their number goes to infinity, which is you're doing the same thing. But this quantity is nothing but the Riemann sum that appears in integration. Some of you might have seen this. And so this reduces to this integral. So the electric field due to this continuous charge distribution at this point P is given by this expression, this integral. So this is an integral over dq over R square R hat. Well, as it stands, of course, this doesn't really look like an integral that you can comprehend actually or evaluate. Well, of course, as we will see, it will assume different forms in for different charge distributions. But for the time being, what you have to understand is that once you write it this way, then they are saying the following. This actually integral amounts to saying you divide this whole charge distribution into small dqs, find the field of each of one of these, and add up the fields of all these fields vectorially using linear superposition. Now this add up these for small dq's which go to 0 is actually meaning integrating. Okay, so this is what does this mean. Evidently when we do exercise examples, things will become much clearer. But the idea is this idea, and as you can see again, just as in the case of multiple point charges, it is built on linear superposition and adding the vector vectorially the electric field of individual charges. Now there are some quantities that we will encounter when we do examples, and you have to understand, and these are the charge densities. Now, since we said that when you have the charges, you have a continuous charge distribution that might be distributed over a volume or a surface or a line. So first quantity is when you have a charge distributed over a volume, and when this distributed evenly, in other words, when that volume, when this charge evenly means uniformly, okay? So it has the same density over all the points in that volume. In this case, we say that the volume charge density, we usually refer to it by rho, is equal to the total charge divided by the total volume. What total volume? The volume through which the charge is distributed. And of course, it will have units of Coulomb per meter square. Now, if your charge is distributed over a surface, then in this case, we use sigma to refer to that charge, and of course, again, evenly distributed over a surface. And in this case, you divide, this sigma is defined as the total charge divided by the total surface over which the charge is distributed. If your charge is distributed over a line, then we have a linear charge density in this case, and we call it lambda usually. And this has the units of Coulomb per meter, and you get it by dividing the total charge that has been distributed over the line by the length over which this charge has been distributed. Another quantity that we will also need when we do calculations in this area is if you have if you want to find dq, this dq, which is the small charge that result when you divide the charge distribution into small element dq. So how is this dq related to the charge density involved? So if you have the charge distributed over a volume, then in this case, each of these dq's will occupy a small volume, and we call it dv. And since rho is the charge per unit volume, then this charge dq, which occupies this volume dv, will have magnitude charge density rho multiplied by dv. Now, if dq is, if the charge is distributed over a surface, then dq in this case will be the charge which occupies a surface, an area equals, small area equals dA. So dq will be sigma multiplied, the surface charge density multiplied by dA. And finally, if dq occupies a small length dl, when the charge is distributed over a line, then in this case, this dq is given by the linear charge density multiplied by this line. Now, we illustrate this by considering an example. The first example that we will consider is the one which is probably technically easiest, which is the charge distributed over a line. So we will consider a line of charge, a thin, thickness is negligible, and it is the charge is distributed over this line of charge, which extends along the x-axis. Its left end is at the distance a from the origin, and its length is L, the length of the line where the charge is distributed over, and so its right end will be at position L plus A. Now, there is a total charge Q. We will be doing this general for any charge, which is, we call it the charge Q in this case, and this is uniformly or evenly distributed over the length of this line, and so it will have a linear charge density lambda, which is just this Q divided by L. Okay. Now our task is to find what is the electric field due to this line of charge at the point P at the origin. Now for definiteness, we will take this charge to be positive, although even for a negative charge it is almost the same, except that the direction of the electric field will be reversed. So let's see how we can work out the electric field of this charge distribution at P.